Thank you. I don't see any of the organizers, but I'm still thankful for inviting me here. It's certainly an honor to speak here today. And what I'm going to talk about is the spectral properties of the Fibonacci Hamiltonians. And I'm going to give a survey of results that were obtained mostly jointly with David Demanik. The very last paper in the series was also jointly with William Gessen, my former graduate student who is currently a postdoc in Rice University. And the object that we're going to study is one-dimensional discrete Schrödinger operator with coupling constant lambda, where the potential is given by this very specific form. If alpha is just any irrational number, then you have a general form of the Sturmian sequence of two symbols. But what I want to do, I want to take alpha to be a very specific number. So the inverse of alpha is going to be the golden mean, that is the continuous fraction expansion is going to have all the coefficients being equal to 1. The reason why I want to take exactly this specific form is because, well, first of all, because that's exactly the operator that was studied by physicists, not even in hundreds but in thousands of papers, not specifically for this operator, but rather for different models related to this specific media, which is the canonical one-dimensional model for a quasicrystal. And secondly, because in this form, this potential can be generated not only as a rotation sequence, but also as a substitution sequence. And the Fibonacci substitution is just a substitution onto symbols of this form. So what I'm going to do, I'm going to start with the symbol 0. After you apply the substitution, you get a word 0, 1. After you apply the same substitution to this new word, you get the word 0, 1 instead of 0 and 0 instead of 1. Then, and so on. So what you can see is that if you at some point arrive to some word in the sequence, then the next word is going to start with exactly the same finite sequence, and therefore the sequence stabilizes. So it makes sense to talk about the limit of this sequence of finite words, and for that limit, we will call that limit to be a Fibonacci substitution sequence. And there is a canonical way to continue this limit to the left, and I'm not going to talk about it because we already have the formula that works nicely, and it's not hard to see that what is given by this formula and what is given by that sequence actually going to give the same whole. So first of all, let's talk about the spectral properties of the spectrum as a set of this operator. And what was known for a while, Andrew Schutter proved that the spectrum must be necessarily a Cantor set of zero measure. For any non-zero coupling constant. In fact, one can say much more. One can say, and this is not yet published, but is correct, I hope, that this set is not just an arbitrary counter set. This is a so-called dynamically defined counter set. For any lambda which is not equal to 0. And let me give the definition. What I'm going to do, I'm going to give kind of a baby version of the definition, and then I will explain what has to be changed and made a little bit more complicated to get the definitions that we actually need. So first of all, I want to describe some specific procedure to construct a counter set. What we're going to do, we'll start with some interval I naught. And we will consider several contractions of this interval into itself, f1, f2, and so on, fk, such that the images do not intersect, and those maps are C1 plus alpha contractions. And then what we can do, we can just consider a map that maps any compact set inside of this interval into the union of the images of that compact set. In the space of all compact sets on that interval is going to be a contracting map with respect to the Hausdorff metric. The space of compact sets with Hausdorff metric is a complete metric space, and therefore there must be a unique fixed point, and that fixed point is exactly a counter set in this case. A counter set is called dynamically defined if it can be obtained as a fixed point of that operator in the space of compact sets. For example, the standard counter set is certainly dynamically defined. You can just consider the two contractions, linear contractions with the coefficient 1/3, and that gives you the standard counter set using this construction. Now, this kind of baby form of the definition is not good enough because sometimes you don't want such a nice regularity. So in this case, roughly speaking, the behavior on this dynamically defined counter set is equivalent to the Bernoulli shift on the space of all sequences of K symbols. What we want, instead of Bernoulli shift, we want topological Markov chains, and that requires some a little bit more complicated explanation that those maps can be defined not on the whole initial interval, but only on some union of those images and so on and so forth. Let me not go into details because this, in spirit, this is exactly what's going on. So dynamically defined counter sets have some very specific properties that distinguish them from arbitrary counter sets. For example, they necessarily have zero measure, and therefore this is now a simple consequence. But also they have some other nice properties. So for example, we can claim that Hausdorff dimension, box counting dimension, packing dimension, whatever reasonable definition of the fractal dimension you can imagine, all of them do coincide for this counter set. So so fractal dimension is well defined, doesn't matter which definition you use. Secondly, local fractal dimension. So I'll go to that. It depends on the coupling constant, and we will describe exactly the behavior of that quantity. So secondly, the local fractal dimension, so the dimension in the neighborhood of any point, doesn't matter how small that neighborhood is going to be exactly equal to the dimension of the whole spectrum of the whole counter set. So also we can claim that this fractal dimension of the set is strictly between 0 and 1, and moreover, as a function of the coupling constant, is going to be analytic function of lambda. In fact, this
can be a general property. There is no lambda in the general.
no, but what you can add here is that each of the contractions is an analytic function of some parameter, and then if you do that, then the Hausdorff dimension of the limit point is going to be an analytic function of the parameter. So that's exactly what we have there. So this is an analytic function of lambda, and actually, in order to claim that, you don't even need to know exactly that this is a dynamically defined counter set, and that was initially obtained by Serge Cantat. Wait, that was 9, I guess. Out of similar but a little bit different observations. Now, a very natural question is exactly what can we say about the value of that fractal dimension. Certainly that value should depend on the coupling constant, and we want to know at least the asymptotics when coupling constant tends to infinity and when coupling constant tends to 0. So when coupling constant tends to infinity, then Hausdorff dimension of the spectrum is going to decrease, and it's going to be decreasing, roughly speaking, as 1 over log of coupling constant. So therefore, what you want to do, you want to take log of coupling constant multiplied by Hausdorff dimension of the spectrum, and what you get is a limit which is equal to the exact constant that can be calculated, and that was done in the paper by Damanik, Embry, myself, and Cherim-Shantsev. And secondly, you want also to know what happens when lambda tends to 0. So you know that the spectrum has 0 measure, and so Lebesgue measure of the spectrum certainly does not depend continuously on lambda, because for lambda equals to 0, you have just a free Laplacian. But at least we want Hausdorff dimension of the spectrum to depend continuously on the coupling constant, and that's exactly what we observe, and this is that was done by in our paper with David not that long time ago. So what else can we say about the spectrum if we just want to restrict our attention to the spectrum as a set? Let's consider the following picture. Let's consider the spectrum as a function of the coupling constant. So we know that it's an interval when lambda is equal to 0, and suppose that you have some gap in the spectrum for some non-zero value of lambda. Now, let's take this gap and let's consider this gap as lambda changes. What can we say about the boundary points of that gap, and what can we say about the rate of opening of how that gap opens when lambda becomes positive? So the claim here is the following. First of all, the boundaries of each of the gaps is a smooth and actual analytic function of the coupling constant, and the size of the gap, so if this gap is u of lambda, then for any particular family of gaps there exists a limit as lambda tends to 0 of the size of this gap that depends on lambda divided by lambda, and moreover this limit certainly does depend on a particular gap, but this limit can be characterized in terms of the label that is attached to that gap, and roughly speaking it will be of order of some constant divided by the absolute value of the label. Now that constant can be uniform.
In the sense of Leibnizian.
Exactly. So
the inequality means that actually you can have 0 in it.
that's exactly what I'm trying to explain right now. So what happens if you take the spectrum and if you take some central part of the spectrum a little bit away from the boundaries, then this constant can be bounded away from infinity and from 0. But as soon as you take that distance to the boundary smaller and smaller, this constant has to be taken smaller and smaller. So we have nice description in this form. Certainly, the convergence here is non-uniform because the sum of all gaps is finite, but harmonic series diverges. Okay. Since we already started to talk about gap labeling, obviously somewhere in the background we're already talking about the density of states measure. So let's now nu sub lambda be the density of states measure that corresponds to the given given coupling constant. So once again, I will list some of the properties, collecting them from the different papers. So first of all, for non-zero coupling constants, the density of states measure is going to be exact dimensional. What it means that for almost every energy, so for nu sub lambda almost every energy, if you take the limit as epsilon tends to 0, of the measure of this interval and divided by you need to take log of this guy and divide it by log of 1 over epsilon. This limit does exist and depends only on lambda. It's the same almost everywhere. And this quantity is exactly the Hausdorff dimension of the density of states measure. Once again, this implies that all possible dimensions of that measure must coincide in this case. And secondly, now you certainly want to ask what is going to be the asymptotical behavior of that dimension of that density of states measure. And once again, it turns out that it tends to 1 as lambda tends to 0. And it tends to 0 as lambda tends to infinity. And moreover, you can say very precisely how it tends to 0. Namely, if you consider this limit, then you can just calculate it explicitly.
That means square root of 5 plus square root of 5.
Thank you.
Okay.
All right. Let me jump here. So if you consider the integrated density of states, the distribution function of this measure, then what you get is a Hölder function. So this is Hölder continuous. In particular, so what it means that there are constants C sum lambda and gamma, well, at this point it will be gamma tilde, sub lambda such that for all values of energy, we have the following. The measure of this interval is not greater than existence of this condition is nice, but what we also want to understand is the behavior of the optimal constants that you can put there. So let me let me set gamma sub lambda to be the optimal Hölder exponent. Namely, I want to take the supremum over all exponents that can be used there. In this case, what we can claim, once again, we can give explicit asymptotics as lambda goes to 0 and as lambda goes to infinity. So we have that it tends to 1/2 as lambda tends to 0. And that's exactly what to be expected, because that's exactly the optimal Hölder exponent for the density of states measure of the free Laplacian. And if you take the limit as lambda tends to infinity, once again it decreases as 1 over log of lambda, and this is going to be this number. Okay. The last question that you should ask here is, okay, what's the relation between all those quantities? And out of the general principles, you know that this one should be the smallest, and the Hausdorff dimension of the spectrum should be the largest, but they in principle could coincide. So the claim is that actually they do not coincide for any lambda which is not equal to 0, and we have strict inequalities. So this is just a definition, and here we have Hausdorff dimension of the spectrum. And in principle, I could add here some transport exponents, but since I don't want to define those objects, I will not talk about that. So that's the results, and I was trying to formulate all those results without any mentioning of any trace maps, dynamical systems, or the proofs. And now I want actually to explain that all those results can be completely reformulated in terms of the dynamical properties of the very particular map, which is called Fibonacci trace map, which I'm going to introduce now.
Maybe you want to add one more, since the dry time martini was discussed on Tuesday. Maybe.
Yes, thank you very much. It's in there, but somehow I missed it. So one more theorem which should be attached to the statement is that dry time martini problem for the Fibonacci Hamiltonian does hold. So all the gaps are actually open that can be opened due to the gap labeling theorem. For any non-zero value of the coupling constant. Did I miss something? Okay. So going to the Fibonacci trace map, let me first define the map. It's just simply looking completely innocent polynomial map of this form. So this is this map, and initially the relation of that map with the properties of the Fibonacci Hamiltonian, it's traditional to give a reference to the paper by Kamata, Kadanov, and Tang, but it was realized by Leo Kadanov before that. There is an unpublished preprint where he studies this map and studies some periodic orbits of this map. But in fact, this map appeared in 19th century already. So let me first explain how it's related to our model, and then I will talk a little bit about 19th century. So what we're going to do, I'm going to consider the transfer matrices, the Schrödinger closed cycle, but you can consider that as it's a discontinuous cocycle over the rotation of a circle, but it's more convenient instead to use the definition of the potential using the Fibonacci substitution. And if you do that, what you want to consider the products of the transfer matrices over the words that are generated by Fibonacci substitution. The lengths of those words are exactly the Fibonacci numbers. And so what you want to do here, you want to consider the products of the transfer matrices for over the first fk elements of the Fibonacci substitution sequence. If you do that, just the fact that the sequence is generated the way it's generated, it gives you a recurrence relation on these matrices. Now, if you want to know the rate of growth of those matrices, for example, since those are SL2R matrices, then determinant is equal to 1, you want to know the traces. So let's say that xk is just, traditionally it's half trace is what people consider. Let's consider the half trace of this matrix. It's not hard to derive from this recurrence relation that you will get a recurrence relation on the traces of the following form. So if you want to calculate xk plus 1, this is just 2xk xk minus 1 minus xk minus 2. That's exactly where this term is coming from. And also, since those matrices are not just some SL2R matrices, you know exactly where they're coming from. You can calculate the traces of the first 3 matrices, and you will get those initial conditions. So what you want to do now, you want to reformulate all that setting in terms of the dynamics of the trace map. Namely, you want to consider the line in 3-dimensional space. And that line is going to be parameterized by the energies and the relation, notice that the point on this line is exactly the point that corresponds to these initial conditions. And then if you want to understand what are the properties of the sequence of traces, you just want to take those initial conditions and to apply the trace map again and again. Now, the relation between the dynamics that you observe and the spectral properties was given by Andreas Schutter also, and the claim is the following. The energy belongs to the spectrum if and only if the positive semi-orbit of the corresponding point, corresponding initial condition, is bounded. It's possible to prove that any orbit must be either bounded, the whole orbit, or it must diverge to infinity either in plus or in either in the future or in the past. And therefore, this gives you a very nice dynamical description of the spectrum that you can now study. Now, at this point, it seems that you have to deal with 3-dimensional dynamical systems, but in fact, you have to deal only with 2-dimensional dynamical system, namely if you consider the following cubic polynomial, then it's easy to check just by hand that this is the first integral of the map. If you apply the map to some points x, y, z, the value of this cubic polynomial is not going to change at all. And for that, there is a nice algebraic reason, actually, and the reason comes from the fact that the trace map, well, there, can be obtained in the following way. Consider a representation of a free group with two generators in SL2C. It's completely determined by the image of the first generator and the second generator. Now let's factorize over the internal automorphisms. You will get the space of invariance, which is exactly the trace of the first image, the trace of the second image, and the trace of the product. That's exactly give you C3, which is in our case just R3. And now what you can do, you can choose a different set of generators in your free group with two generators. In our case, the changes of generators is given exactly by the Fibonacci substitution. The changes of generators induces the polynomial change in the space of invariance, and for that particular change of generators, this is exactly the polynomial map that will be induced. Out of the general reasons, any change of generators in this picture is going to preserve the trace of the commutator of the images. And what you have here is exactly the trace of the commutator. So there is an internal reason why that integral does exist. But since this integral does exist, we can restrict our attention to the level surface of that integral. So what we can do, we can consider surfaces given by the level surfaces of this integral, and this is approximately how it looks like. So if I want to draw the surface that corresponds to zero value of the coupling constant, this is a so-called Kelly cubic. So roughly speaking, I'll have to deal with the surface that looks like this. So you will have some internal part that is topologically a sphere with 4 conic singularities and 4 unbounded parts. And then, so this is a sub-knot. And if you turn on the coupling constant, the corresponding surface becomes smooth and non-compact, and it's easy to see that the line of initial conditions is exactly inside of one of those, inside of the corresponding surface. So somewhere here you have that line of initial conditions. So that's the picture. Now you can restrict your attention to the map, which is restricted to this level surface, and therefore you actually have two-dimensional dynamical system. All you need to do now is to understand what is the set on this line that does not go to infinity under the positive iterates. In order to do that, we can do the following. We will consider the set of all points with bounded orbits, not necessarily with bounded semi-orbits, but the whole orbit is going to be bounded. So let lambda sub lambda be the set of points such that the whole orbit is bounded. Then it turns out that this set is a hyperbolic basic set, so it's hyperbolic, locally maximal, totally disconnected, set, intransitive set for T sub lambda. What is hyperbolicity? I believe that hyperbolicity of a cocycle is something which is familiar. So let's just consider our map which acts by its differential on the cocycle formed by the tangent spaces at the points of this set. You have a cocycle, hyperbolicity of that cocycle is exactly equivalent to the hyperbolicity of this map on this set. Okay, so this theorem was initially proved by Martin Kazdagley in 80s for large values of coupling constants. We proved for small values of coupling constants, and then almost simultaneously, Serge Cantat proved it for all values of coupling constants. So we do have hyperbolicity here. Now, it turns out that if you have that description, it's really easy to understand what is the set of points that have positive bounded semi-orbits. That's exactly the set of points that are going to accumulate to our invariant set in the future. And in hyperbolic dynamical systems, the description of the set is very nice and simple. It turns out that every point here has a curve, smooth curves, in our case analytic curves, that goes out of that point. The set of all those curves form nice foliation, or better to say lamination, that locally looks like a product of a Cantor set by an interval. So somewhere here you have some Cantor set, and you have lots of curves, and those curves are going to intersect our line, and that intersection is exactly the set which is equivalent to our spectrum. The only thing that is missing here is transversality of these curves and this line of initial conditions, and that's exactly one of the main points of our work. Is transversal to the line of initial conditions. Amazingly enough, this is completely non-trivial statement. We could not prove that directly just by constructing some cones using some geometrical approach. So what we had to do is actually to use spectral theory and indirectly derive from spectral theory that you have transversality. Namely, if you complexify all this picture, and if you do not have transversality, you must have a tangency. And if you have a tangency, then a small perturbation gives you some contradiction in the following sense. The intersection between analytic curves can be treated as zeros of some analytic function. And if you have zeros of analytic function, then those zeros, due to the Horvitz theorem, cannot disappear. So if they seem to disappear, it means that they went to the complex domain. But if they went to the complex domain, the description of Schuto actually can be also complexified, and that would imply that the spectrum would contain some energies that are not real, which is impossible because we know that for our self-adjoint operator, the spectrum must be a subset of the real line. So this is highly non-geometrical argument, which was surprising to me personally. So that's the idea how you can deal with the spectrum, and then you can work with this dynamical system to derive all those properties that I mentioned. But in fact, you can see not only the spectrum, but also the density of states measure out of this geometrical picture. Namely, you may want to define the measure of maximal entropy for this map. The measure of maximal entropy is such a measure that the metric entropy of that measure is equal to the topological entropy of the map. Fortunately, in order to define the measure of maximum entropy, I do not need to define any of those words. So and it can be defined for this trace map restricted to S sub lambda as the following limit. So what I want to do, I want to take all periodic orbits of the map, and I want to put an atomic measure to each of those periodic orbits of period n. And then I want to normalize to get a probability measure. And then I want to take the limit, and it turns out that this limit must exist, and that limit is exactly the measure that I'm looking for.
What is in the denominator? You have the number.
Okay.
What is n? What is small n? What is small n?
What I consider periodic orbits of period n for this map, and I consider all the periodic orbits of period n for this map, and I put a delta measure into each of that points, and then I normalize. This is so what I'm going to construct. I'm going to construct an invariant measure for my trace map restricted to S sub lambda.
On each of the points, so if it's a periodic orbit, you put an n on every point.
Yeah, this map has lots of periodic orbits. I fix some period. I consider all periodic.
You count it 10 times. Every orbit is counted.
No. You have a finite number of orbits with the given period.
Yes, not necessarily smallest period. So I take all the periodic orbits of this map of given period n. And then I just put atomic measure to each of them and normalize. And then it turns out that if n grows, you get more and more points. Actually, the number of points grows exponentially fast with the period. And it turns out that there exists a limit. So sometimes this measure is called Margulis measure, sometimes it's called Bowen's measure. In any case, this is a measure of maximum entropy. Yes?
So orbits of period n have counted.
Say it again?
The period should be strictly n.
No. Any period, but actually it doesn't matter because all the orbits of smaller period will be, since you have exponential growth, either definition will work. Okay. So the claim is that, roughly speaking, this measure of maximum entropy is responsible for the density of states measure of the Fibonacci Hamiltonian. Namely, if I take this measure of maximum entropy and take the projection, so somewhere here I have some measure on my set, and I take the projection along the stable leaves to the line of initial conditions, I will get some other measure on this line, and this line is, roughly speaking, the line where my spectrum lives. And it turns out that what you get is going to be the density of states measure. I have to be very careful here because this projection is not uniquely defined, so the same leaf may intersect this curve in many different spots. So the formal statement is the following. If you take this projection and you take this projection to be continuous, what you get is not exactly the density of states measure, but it's a measure which is going to be proportional to the density of states measure. And once again, certainly I need to remember that there is a parameterization of that line, so on, but I hope that it's clear what I mean here.
Proportional means that you count more than once?
No, proportional just means that it's the same measure up to the constant multiplier locally. So let me take some piece here. Let me project it nicely. What I get a measure on the part of the spectrum. If I take the restriction of the density of states measure to the same part of the spectrum, I will get a measure which differs from the measure given by this projection by a multiplicative constant.
They're both probability measures.
Say it again?
They're both probability measures.
Since here you have only part of the density of states measure. So here's my spectrum. And if my projection gives you only
It's only defined in a kind of
it's defined only in some interval inside of the spectrum.
Take another interval and you get another. Okay.
Yes. So if you take another projection, you get another interval and so on. So essentially, actually, you can choose carefully the projection such that it gives you exactly what you need. But I really don't want to go into those details. So ideologically, this is exactly what you want. And people know a lot about measures of maximal entropy for the hyperbolic sets. In particular, they do know that those measures must be measures of that are exact dimensional. They know that the Hausdorff dimension of the measure of maximum entropy depends analytically, in this case, on the parameter. So all the same claims can be made for the density of states measure for the Fibonacci Hamiltonian. And finally, I want to give an explicit relations between all the quantities that we considered and spectral quantities and dynamical quantities that can be formulated in terms of the trace map. So this is the relation. So first of all, the simplest one is just the Hausdorff dimension of the spectrum. This is exactly half of the Hausdorff dimension of the hyperbolic set that we get there. Secondly, the Hausdorff dimension of the density of states measure, this d sub lambda thing. This is exactly the ratio of the topological entropy of the map to the Lyapunov exponent, unstable Lyapunov exponent of the measure of maximal entropy. And the topological entropy of this map is just a number. It does not depend on lambda at all. So what you have here is this mysterious coefficient that appeared in many of the limits.
Actually, log of frequency. Log of golden mean.
Yes, exactly.
Golden mean, log of frequency.
Now, if you take the optimal Hölder exponent, then you get once again topological entropy divided now by the Lyapunov exponent of periodic measure, but you have to take the supremum of all the Lyapunov exponents over all atomic ergodic measures. And well, you can ask what happens if you replace supremum by infimum here. I will not write it, but what you get is exactly the upper transport exponent. So all those things fit each other nicely. And in fact, they can be included into the same picture using the so-called thermodynamical formalism. Well, I don't have much time, so let me skip a couple of definitions and kill half of the audience. But nevertheless, I really want to show the picture. So what I'm going to consider, the potential psi of x, which is going to be minus log of the log of the expansion of the trace map.
Where? E to the power? What is?
No, what I'm doing here, I'm taking the differential of the trace map
and then E
restricted to the unstable direction. So since we have a hyperbolic set, every tangent space is split into stable and unstable directions. So I just want to take the most expanding direction in a sense.
it's not n, it's unstable.
It's unstable, yes. Now, if I do that, what I can consider so-called pressure function. This is a topological pressure that corresponds to this potential multiplied by t, and this is going to be a function of t. So sometimes it's called Bowen function Sometimes it's called pressure function. And what it means that what you want, now I give not a canonical definition, but what the definition that follows from the variational principle. I consider supremum over all invariant ergodic measures of the measure theoretical entropy plus t multiplied by the integral of this potential over that measure. And it turns out that there exists unique ergodic measure mu sub t such that this pressure function actually, this supremum is actually attained for this measure. This measure is called equilibrium measure for this potential. And the nice properties of this pressure function were studied for hyperbolic set by Reuel, Sinai, Bowen, Perry, and other people. And in particular, it's known that in our context, this is going to be strictly convex decreasing function, which is analytic. And so roughly speaking, this is how the graph of the function is going to look like. So this is a function, and notice that if you take zero potential, then what you get instead of pressure function, the value is going to be exactly the topological entropy of our map. Now, the value of the parameter where the pressure function is equal to 0 due to the result by Manning-McCluskey is equal exactly to the Hausdorff dimension of the corresponding counter set, and in our case, this is the Hausdorff dimension of the spectrum.
The asymptote, yeah.
No,
The asymptote.
this is an asymptote.
Straight line with asymptote, yes.
This is okay.
There are several lines.
Okay, this is a graph,
Yeah.
and this one is just asymptote for the graph. This is a straight line. Well, I was trying to make it a straight line. Okay, now, if you take the tangent line at this point, then somewhere here, it will intersect the horizontal line, and this point, this value of the parameter is exactly the Hausdorff dimension of the density of states measure. Now, if you take this point and take the line which is parallel to this asymptotic line, then what you get is exactly the optimal Hölder exponent. And now if you take this point and take the line which is parallel to another asymptote, what you get is exactly upper transport exponent. So from this picture and from the convexity of the pressure function, you can see that we have strict inequalities between those quantities for all values of the coupling constant, and it follows strangely from thermodynamical formalism for hyperbolic dynamical systems. All right, I still have 5 minutes, right? No? 3? Okay. Then let me just show the pictures, and let me try to can I please show the picture? Thank you. So the very last 2 minutes I'm going to spend to explain an open problem. After we studied in detail one-dimensional case, what we want to understand the properties of the say two-dimensional. We want to understand the properties of two-dimensional quasi-crystals, and the most reasonable model is, for example, Laplacian on the graph given by vertices of the Penrose tiling. But this is a notoriously hard problem, so let's cheat a little bit, and let's consider the square Fibonacci Hamiltonian. And it's known that for the separable potential, the spectrum, this is a general statement, works not necessarily for Fibonacci Hamiltonian, the spectrum is going to be the sum of one-dimensional spectra, and the density of states measure is going to be the convolution of one-dimensional density of states measure. So let's first look at the pictures that I'm going to show were produced by Mark and Bree, this is the picture of the spectra of just one-dimensional Fibonacci Hamiltonian. So this is the axis of energies, and this is the axis of coupling constants. And for each coupling constant, you have a counter set. If you stack all those counter sets together, this is what you get. And you can see that our claim about linear opening of the gaps really seems to be justified numerically, and a lot of statements. What I want to do now, I want to take this picture and I want to consider the sum of that counter set with itself in order to understand what is going to happen for the two-dimensional square Fibonacci. This is what computer shows. So it shows that for small values of coupling constant, you actually have an interval as a spectrum. For large values of coupling constant, it looks like a counter set, and something funny happens in between. And if you take the three-dimensional version, you will get very much similar picture. So what we can do, it's really not hard to justify that for large values of coupling constant, you get a counter set. It just follows from the fact that the sum of two dynamically defined counter sets with small Hausdorff dimensions is also counter set of zero measure. It's harder to justify that you have an interval, but that was also done in our paper with David that uses the notion of thickness of counter set, and the spectrum of Fibonacci Hamiltonian has thickness that tends to infinity. I don't have time to explain what it is, but in a sense, my feeling is that it's kind of analog of homogeneity for counter sets of zero measure, in a sense. So it's possible to prove formally that in this part of the picture we do have an interval, but when we get to that middle ground region, we don't have, unfortunately, a rigorous result, but we have a pretty good guess. So we believe that the spectrums there topologically should be a so-called counterval. A counterval is a compact set that consists of uncountably many connected components, such that the interior of that set is dense in the set, and none of the connected components is isolated. Now, how should you think about such a set? Think about a counter set where, for a dense countable set of points, you just blow those points up a little bit in such a way that you, instead of those points, you inserted some tiny intervals. You will get something that looks like a counter set. It contains lots of points, but densely it will also contain intervals instead of points. So this is a counterval, and that guess is justified by general statement that typically, generically, if you have a family of couples of dynamically defined counter sets where sum of Hausdorff dimensions is just a little bit larger than 1, then generically you will get a counterval for some intervals in the space of parameters. But unfortunately, the statement is, as I said, for generic families, and our family is not generic at all. It's very specific family. There is no way to make any kind of perturbations, and so we cannot apply that result. Nevertheless, it's certainly an indication that it should be counterval, and it would be really interesting to prove that. So let me stop here.
Are there any questions, comments? You look at the case of a very particular alpha. What's happening when you change the alpha? How the results depend on alpha?
Nice question. So first of all, if alpha is quadratic irrationality, then everything that I said which does not involve any specific numbers does hold.
Even quadratic with just quadratic n, you mean? Unbounded.
If alpha is quadratic irrationality, or in other words,
yes. Okay. Yeah.
That everything works, and in principle, one could calculate specifically the numbers that I mentioned, the specific rates of.
And they will depend on alpha.
They will depend on alpha. If you consider the general Sturmian Hamiltonian, then situation changes completely. In particular, there are examples by some people in the audience, by the way, that for some specific Sturmian potentials, you don't have the counter set to be dynamically defined. For example, box counting and Hausdorff dimensions can be different, and so on and so forth. So they have much more complicated properties. Nevertheless, we believe that there exists a very much similar description, but instead of just one map, you have to consider countably many maps. Each map corresponds to the specific coefficient in the continued fraction expansion. In our case, all the coefficients were equal to 1, so you just apply the same trace map all the time. But if you have different maps, you have applied a sequence of different maps. And what is true is that if an initial condition is a point such that it does not go to infinity, it remains bounded under the application of the sequence of maps, that the corresponding energy belongs to the spectrum. But it's certainly much harder to analyze.
Does the Hölder continuity also depend on?
No, this is the result by thank you. By a student of David who actually showed that for depending on the alpha, you can or cannot have Hölder continuity, and for many values of alpha, you will not have Hölder continuity.
But for those, you will it be depend on what kind of alpha you take, or it will be the same for all of the alpha to which
it will certainly depend on alpha, because even the asymptotics as lambda tends to infinity depends on alpha already.
Any other questions? If not, let's thank the